The cosmos holds secrets that defy our understanding of reality itself. Our universe is not static but stretching, growing larger every moment. And this expansion hides 25 profound mysteries that challenge everything we think we know. By the end of this journey, you will grasp the true scale of our ignorance and the thrilling frontiers of modern cosmology. We will confront the invisible forces shaping our cosmic fate and ask if the stars themselves are hiding answers to questions we have not yet learned to pose. What part of this vast unknown captures your imagination the most? Our universe is filled with a ghost. We cannot see it, touch it, or measure it with any instrument we have yet devised, yet its gravitational pull is the only thing keeping galaxies from flying apart. This is the first and perhaps most fundamental mystery, the nature of dark matter. Its story begins not with a direct observation, but with the behavior of things we can see. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She found that stars at the outer edges of these galaxies were orbiting just as fast as those near the center. This was completely unexpected. According to the laws of gravity, the visible matter in a galaxy, all its stars and glowing gas, does not provide enough gravitational glue to hold these swiftly moving outer stars in place. They should have been flung out into the void, yet something invisible, something with immense mass, was providing the extra gravity to hold everything together. We call that something dark matter. Further evidence comes from a phenomenon called gravitational lensing. The immense gravity of dark matter warps the fabric of space-time itself, bending the light from distant galaxies as it travels toward us. Astronomers see these distorted, stretched, and sometimes duplicated images of faraway objects, and by mapping this distortion, they can literally trace the outline of the invisible dark matter causing it. It is like seeing the silhouette of a person by watching how the air ripples around them on a hot day. So what could this mysterious substance be? The leading candidates are particles that barely interact with normal matter. One possibility is WIMPs, or weakly interacting massive particles. These are theoretical heavy particles that would only interact through gravity and the weak nuclear force, making them incredibly difficult to catch. Another candidate is the action, a particle that is trillions of times lighter than an electron, but could exist in such vast numbers that it adds up to the required mass. Think of it like trying to find one specific, silent grain of sand on every beach on Earth. Only this grain of sand can pass right through solid rock without a trace. This is the core of the problem. Dark matter makes up about 27% of the entire mass and energy content of the cosmos. It is the cosmic scaffolding upon which galaxies are built, the hidden architect of the large-scale structure of the universe. Yet after decades of searching with exquisitely sensitive detectors placed deep underground to shield from cosmic rays, we have not directly detected a single particle of it. We see its shadow everywhere, a giant presence dictating the fate of everything we see, while it remains utterly, frustratingly, and completely invisible to us. What kind of reality allows for something so fundamental to be so permanently hidden from our senses? Just as we grapple with an invisible cosmic scaffold, we face a force even more baffling. The universe is not merely expanding, it is accelerating, flying apart at an ever-increasing rate. This discovery in the late 1990s was so shocking it earned the Nobel Prize. Two independent teams of astronomers were measuring the distances to far-off supernova, the brilliant explosions of dying stars. They expected to find that the expansion of the universe was slowing down, gradually braked by the collective gravity of all matter. Instead, they found the opposite. The most distant stellar explosions were fainter than they should have been, meaning they were farther away than any model predicted. The only explanation was that the fabric of space itself was stretching faster and faster over time. Something was overpowering gravity, a mysterious repulsive force we now call dark energy. This dark energy is not just another component of the cosmos, it is the dominant one. It constitutes about 68% of the entire energy budget of the universe. Think of it this way: if the total cosmic pie were divided into slices, dark energy would be the vast majority, dark matter a significant wedge, and all the stars, planets, and galaxies we see and love would be nothing more than a few tiny crumbs on the plate. So what is this force that is relentlessly pushing the cosmos apart? The leading explanation is the cosmological constant, an idea that Albert Einstein himself proposed and then later called his greatest blunder. It represents a constant energy density, an inherent property of the vacuum of space itself. Empty space is not truly empty according to quantum physics, but a seething foam of virtual particles popping in and out of existence. This quantum activity could generate a repulsive force, a steady pressure woven into the fabric of reality. However, there is a colossal problem. When physicists calculate how strong this vacuum energy should be, their theoretical predictions are off by a factor of 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the entire history of science. The alternative theory is called quintessence. This proposes that dark energy is not a constant but a dynamic field, a fifth fundamental force that permeates the cosmos and whose strength could change over time. It might be weakening or it might be strengthening. The ultimate fate of the universe hinges on which of these ideas is correct. Will the acceleration continue at a steady pace, leading to a cold, dark, and lonely end? Or could the quintessence field grow so powerful that it tears apart galaxies, stars, and even atoms themselves in a final event known as the Big Rip? We are left with a profound irony. The force that makes up most of our universe is a complete enigma, its true nature the second great mystery of our expanding reality. This growing acceleration is not the only puzzle. A third mystery is creating a rift in cosmology itself, a conflict over the very speed of the cosmic expansion. We call this the Hubble Tension. At its heart is a simple yet profound question: how fast is the universe expanding right now? Astronomers have two primary ways to measure this rate, known as the Hubble constant. One method looks at the local, modern universe. By observing the pulsing of certain stars and the explosions of specific supernovae in nearby galaxies, they can measure distances and velocities with impressive precision. This gives them a direct present-day measurement of the expansion speed. The other method looks back to the infant universe, to the faint afterglow of the Big Bang known as the cosmic microwave background. By meticulously mapping the tiny fluctuations in this ancient light, scientists can calculate what the expansion rate must have been in the beginning to create the universe we see today. Here is the problem: these two methods, one local and one ancient, do not agree. They are giving us two different, stubbornly inconsistent answers for the same fundamental number. It is as if you used two different clocks to time the same race, and one clock insists the runner is significantly faster than the other claims. This is not a small discrepancy. The error bars have shrunk with more precise measurements, yet the gap remains, suggesting this is not a mere mistake but a potential flaw in our understanding of cosmic physics. This tension leads us directly into the fourth and perhaps most existential mystery, the ultimate fate of the cosmos. The expansion rate and the nature of dark energy dictate how our universe will end. If dark energy remains a constant force, as the cosmological constant suggests, the acceleration will continue steadily. Galaxies will be pushed ever farther apart, stars will burn out, and the universe will approach a state of maximum entropy, a dark, cold, and lifeless equilibrium known as the Big Freeze or heat death. But if the Hubble tension points to a more dynamic form of dark energy like quintessence, other fates are possible. Should this repulsive force grow stronger over time, it could eventually overcome all other forces. First, galaxy clusters would be torn apart, then individual galaxies, the gravitational bonds holding stars together, would snap. Planets would be ripped from their suns. In the final moments, even atomic nuclei would be shredded in a catastrophic finale called the Big Rip. There is a third, older possibility, the Big Crunch. If the density of matter were high enough, gravity could eventually reverse the expansion, pulling all of space, time, and matter back into a singular point. Current evidence for dark energy makes this outcome seem unlikely, but our incomplete understanding leaves a sliver of doubt. The resolution of the Hubble tension is the key that unlocks our cosmic destiny. Is the discrepancy a hint of new particles, a strange property of dark energy we have not yet imagined, or a sign that gravity itself works differently on the largest scales? Until we solve this puzzle, the final chapter of our universe's story remains an open question, its ending written in a language we are still learning to read. This asymmetry between matter and antimatter is a crack in the foundation of reality, a crack that allowed us to exist. For every particle of matter the Big Bang created, it should have created an identical particle of antimatter. Think of antimatter as the perfect, malevolent twin of matter, identical in mass but opposite in charge. When a matter particle meets its antimatter counterpart, they annihilate each other in a flash of pure energy. If the early universe had been perfectly symmetrical, this mutual destruction should have been total, leaving behind a cosmos filled with nothing but radiant energy. There would be no atoms, no stars, no planets, and no one to wonder why. Yet here we are in a universe made almost entirely of matter. Something must have broken that perfect symmetry, allowing one single, solitary matter particle to survive for every 1 billion matter-antimatter pairs that annihilated. That tiny 1 in a billion surplus is everything we are made of. The entire observable universe is built from the ashes of that near-total annihilation. So what tipped the scales? The leading clue is a phenomenon known as CP violation. C and P stand for charge and parity. Charge conjugation means swapping every particle with its antiparticle. Parity reversal is like looking at the universe in a mirror, flipping left and right. For a long time, physicists assumed the laws of physics were symmetric under both these operations. A reaction involving particles should look exactly the same if you replaced them all with antiparticles and viewed it in a mirror. But in the 1960s, experiments with certain subatomic particles called kaons showed this was not always true. The mirror image of a particle decay was not identical to the decay of the antiparticle. It was a tiny, subtle difference, but it proved that nature has a tiny, built-in preference for matter over antimatter. This CP violation provides a mechanism for the imbalance, but there is a problem. The amount of CP violation we have observed in laboratory experiments is far too small to account for the overwhelming dominance of matter in the cosmos. It is like finding a single dropped coin when you need to explain a vast planetary treasure. The hunt is now on for new, stronger sources of this symmetry breaking. At laboratories like CERN, physicists are smashing particles together at incredible speeds, studying the behavior of exotic particles like beauty quarks, searching for any slight deviation, any hint of a process that favors matter just a little bit more. They are essentially recreating the conditions of the very early universe to watch the symmetry break in real time. Finding the source of this cosmic bias is more than an academic exercise, it is a quest to understand our own existence. Why does the universe, at its most fundamental level, have a law that permitted us to be here at all? The answer is still hiding within the quantum mirror, in the subtle flaws of its reflection. This matter-antimatter imbalance is a fundamental crack in reality, but another, even more dramatic event may have shaped the cosmos in its very first moments. The theory of cosmic inflation proposes that the universe underwent an incredible growth spurt, expanding exponentially in the tiniest fraction of a second after the Big Bang. To grasp this, picture a subatomic speck of space ballooning to the size of our entire observable universe faster than a blink. This concept solves two major puzzles about the cosmos we see today. The first is the horizon problem. When we look at the cosmic microwave background, the oldest light in the universe, it has the same temperature in every direction we look. This is deeply strange because those distant regions of the sky were never close enough for heat to travel between them, not even at the speed of light. It is like walking into a room and finding 2 cups of coffee, one on each side, that have cooled to the exact same temperature without ever having been in contact. Inflation solves this by suggesting that these vastly separated regions were once snuggled up together in a tiny, ultra-hot patch. The inflationary burst then stretched them far apart, locking in that uniform temperature before they could lose contact. The second puzzle is the flatness problem. Our universe appears remarkably flat on large scales, meaning the fabric of space-time is not curved back on itself like a sphere. For the universe to be this flat after billions of years of expansion, its initial conditions had to be fine-tuned to an absurdly precise degree. Inflation naturally flattens the cosmos, just as blowing up a balloon makes its surface appear flatter and flatter from the perspective of a tiny ant living on it. The most compelling evidence for inflation would be the detection of primordial gravitational waves. These are not waves in water or air, but ripples in the very fabric of space-time itself, generated by the violent quantum jitters of the inflationary field. These waves would have left a unique, swirling pattern called B-mode polarization imprinted on the cosmic microwave background. Finding this pattern would be the smoking gun, a direct echo from the universe's first fleeting moment of existence. Experiments at the South Pole and in space are constantly scanning the ancient sky for this faint signature. This search is a direct attempt to listen to the vibrations of creation, to understand the very mechanism that set the stage for every galaxy, star, and planet that would ever form. Floating through the void, a single, invisible particle carries more energy than a professionally thrown baseball, all packed into a subatomic speck. These are ultra-high-energy cosmic rays, and their existence is a profound mystery. They are atomic nuclei, stripped of their electrons, racing across the universe at velocities approaching the speed of light. When one of these rare projectiles slams into Earth's upper atmosphere, it creates a spectacular cascade of secondary particles, a shower that can spread over miles. The energy involved is almost incomprehensible, millions of times greater than what we can achieve in our most powerful particle colliders, like the Large Hadron Collider. Nature is hurling these particles at us with a force we cannot hope to replicate, and we have no clear idea what cosmic cannon is firing them. The central problem in solving this mystery is that cosmic rays are not straight-shooting bullets. They are charged particles, which means they are deflected and sent on winding, chaotic paths by the magnetic fields that permeate the space between galaxies. By the time one reaches Earth, its trajectory is a hopelessly tangled mess, pointing back not to its source, but to the last bend in its long and twisted journey. It is like trying to find the origin of a leaf caught in a hurricane by looking at the spot where it finally landed. So, where could such incredible accelerators exist? The prime suspects are some of the most violent and energetic objects in the cosmos. Active galactic nuclei, the supermassive black holes at the hearts of galaxies, are leading candidates. As these black holes devour vast amounts of matter, they can create powerful jets of plasma stretching for thousands of light years. Magnetic fields within these jets could, in theory, act as a natural particle accelerator, focusing and energizing stray atomic nuclei to these unbelievable speeds. Another possibility involves gamma-ray bursts, the most explosive event since the Big Bang itself. The cataclysmic collapse of a massive star or the merger of 2 neutron stars could unleash shock waves powerful enough to impart such tremendous energy. Yet, when astronomers point their telescopes toward the suspected locations of these events, the evidence is often inconclusive. Some of these ultra-high-energy particles seem to arrive from empty, seemingly quiet patches of space, suggesting there are accelerators out there we have not yet even imagined. What colossal, hidden engines are capable of such a feat, and what can their existence teach us about the most extreme laws of physics governing our universe? We are not alone in wondering who might be calling. Across the vast, silent ocean of space, two signals have echoed, one modern and frantic, the other ancient and singular, both defying easy explanation. The first are fast radio bursts. These are blasts of cosmic radio waves that release more energy in a single millisecond than our Sun puts out over 3 entire days. They travel for billions of years from distant galaxies, and then, in a literal flash, they are gone. When the first one was discovered in archived data in 2007, it was so bizarre that astronomers debated if it was a glitch. Now we know they are real, and they are happening all the time. Some of these bursts are one-off events, cosmic tantrums that scream once and then fall silent. Others are repeaters, firing off signals again and again from the same patch of sky. So what natural engine could possibly be this powerful and this fast? The prime suspect is a magnetar, a type of neutron star with a magnetic field so intense it could erase a credit card from halfway across the solar system. A starquake on the surface of such an object, a sudden cracking of its crust, could theoretically unleash a focused blast of radio waves that we see as a fast radio burst. Yet the sheer power of the most intense burst still pushes the limits of this explanation, leaving the door open for more exotic possibilities, even the distant, faint hope of advanced alien technology. This brings us to the second legendary signal, one that predates these bursts by decades. In August 1977, a radio telescope in Delaware, Ohio, part of the Search for Extraterrestrial Intelligence program, was scanning the sky. A volunteer named Jerry Amon was reviewing the computer printout when he saw a string of data so remarkable he circled it and wrote one word in the margin: "Wow." The signal was strong, it lasted for 72 seconds, and it was narrowband, meaning it was concentrated on one specific frequency. Just the kind of signal scientists predicted an artificial, extraterrestrial transmission would produce. It came from the direction of the constellation Sagittarius and has never, ever been heard again. Despite countless follow-up observations, the silence has been absolute. Was it a one-time cosmic fluke, a reflected signal from a passing human satellite? Or was it a genuine hello from the stars, a message that swept past us and vanished back into the eternal quiet? The WOW signal and fast radio bursts represent two sides of the same deep mystery. We are listening to a universe that seems to whisper and shout, sending us coded messages we are only beginning to hear, their meaning tantalizingly out of reach. Our galaxy is not wandering aimlessly through the cosmos. The Milky Way, along with our entire local group of galaxies, is caught in a vast river of motion, all flowing toward a single, unseen destination. This is the mystery of the Great Attractor, a colossal gravitational anomaly located some 250 million light-years away in the direction of the Centaurus constellation. Its pull is so immense that it is drawing our galaxy and thousands of others toward it at a staggering speed of over 2 million kilometers per hour. For a long time, the true nature of this cosmic beacon remained hidden, simply because it lies directly behind the plane of our own galaxy. Astronomers call this region the zone of avoidance. From our vantage point, the dense band of stars, gas, and dust that makes up the Milky Way's disk acts like a cosmic curtain, completely blocking our optical view of the universe beyond. It is the ultimate blind spot in our map of the heavens. Trying to see the Great Attractor with a traditional optical telescope was like trying to see a distant city through a thick, permanent fog. The breakthrough came when we learned to look with different eyes. Space-based observatories that see in X-ray and infrared light can peer through this obscuring veil. X-rays penetrate the dust, revealing the hot, glowing gas that often surrounds massive galaxy clusters. Infrared light, less affected by interstellar dust, uncovers the faint glow of stars themselves. These new views unveiled a staggering truth. The Great Attractor is not a single, monstrous object, but the heart of an enormous supercluster of galaxies, a nodal point in the cosmic web we call the Laniakea supercluster. Our own Milky Way is merely a suburban speck on the outer fringes of this vast metropolitan structure, which contains over 100,000 galaxies all bound together by gravity. Yet, even this colossal concentration of mass does not fully account for the immense pull we feel. The river of galaxies seems to be flowing toward something even greater, a more distant and massive structure known as the Shapley Attractor, which lies beyond. This reveals a universe of nested pulls and tides where we are drawn to the Great Attractor, which is itself drawn toward something else in an endless cosmic dance. What ultimate source of gravity commands this vast, silent flow, and what will we find when we finally map the entirety of the currents that guide our journey through the void? Even our own spacecraft sent to explore the solar system began to act strangely. As the Pioneer 10 and Pioneer 11 probes sailed beyond the orbit of Neptune, their trajectories began to deviate from the precise paths calculated by mission control. A tiny, persistent, and entirely unexpected force seemed to be acting upon them, a faint but constant deceleration back toward the Sun. This was the Pioneer anomaly. For decades, this minuscule drift, a pull equivalent to just 1/10,000,000th of the gravity we feel on Earth, baffled physicists. It was a whisper in the data, a ghost in the machine. Was it a sign of some unknown physics, a flaw in our understanding of gravity itself at the outer reaches of the solar system? Theories flourished. Some proposed that dark matter was clustered around our Sun, its gravity gently tugging on the distant probes. Others suggested modifications to Einstein's theory of general relativity, a new law that would reveal itself only over vast interplanetary distances. The anomaly became a classic scientific mystery, a puzzle that seemed to point toward a fundamental discovery. The solution, when it finally came, was not a revelation of new physics, but a triumph of meticulous, old-fashioned detective work. The culprit was not a cosmic force, but the spacecraft themselves. These probes are powered by the heat from radioactive plutonium, and that heat had to go somewhere. Scientists realized that this thermal radiation was not perfectly symmetrical. A tiny, anisotropic push was being generated as the heat radiated preferentially from one side of the craft. It was the spacecraft's own warmth, gently but relentlessly pushing them backward. Think of it like holding a warm light bulb in the palm of your hand. You cannot feel it, but in the frictionless void of space, even that faint photon pressure can, over years and billions of miles, add up to a measurable change in velocity. The Pioneer anomaly stands as a profound cautionary tale. It reminds us that in the pristine laboratory of deep space, even the most trivial of effects, the heat from a power source, can masquerade as a cosmic mystery. It teaches us humility, showing that before we invoke dark matter or rewrite the laws of physics, we must first ensure we are not simply seeing our own reflection in the data, a ghost we ourselves sent into the void. Far beyond the orbit of Neptune, in the cold, dark fringes of our solar system, a vast ring of icy worlds abruptly ends. Astronomers call this the Kuiper Belt, and its sudden, unexplained boundary is known as the Kuiper Cliff. Just past a distance of about 50 astronomical units from the Sun, the population of these frozen objects plummets. It is as if you were walking through a dense forest and suddenly stepped onto an empty plain with the trees stopping in a perfectly straight line. This is not what our models of solar system formation predicted. The primordial disk of dust and gas that birthed the planets should have faded away more gradually, leaving a sparse but steady population of objects stretching much farther out. The observed drop-off is too sharp, too clean to be a natural conclusion. So what or who built this cosmic wall? One compelling theory points to the gravitational hand of a hidden architect. A planet large enough to be a true world may be lurking in the profound darkness, its gravity shepherding the orbits of these distant icy bodies. This hypothetical planet 9, with a mass perhaps 10 times that of Earth, would orbit the Sun on a long, elliptical path that takes it hundreds of astronomical units away. Its immense gravitational influence could have swept its orbital neighborhood clear over billions of years, either flinging smaller objects inward toward the Sun or hurling them out into interstellar space. This would carve out that distinct cliff we observe today. The evidence for this unseen giant is not just this emptiness, but also the peculiar, clustered orbits of a handful of extremely distant objects that all seem to be tilted and aligned in a way that suggests a massive, distant perturber. Yet, if it exists, why have we not found it? The search is astronomically difficult. Such a planet would be incredibly faint, reflecting only the tiniest slivers of sunlight, and its enormous orbit means it moves agonizingly slowly across the sky. Finding it is like searching for a single, dim, and slow-moving needle in a cosmic haystack the size of the entire solar system. An alternative theory suggests the cliff is a fossil, a relic from the solar system's violent birth. Perhaps the protoplanetary disk from which we formed simply had its own natural edge, a place where the density of material dropped off sharply. The gravity of a passing star in our Sun's early stellar nursery could have stolen away the outer material, or maybe the processes of planet formation never got started beyond that boundary. This would make the cliff a frozen monument to the initial conditions of our cosmic neighborhood. The true answer remains suspended between these ideas, a ghostly presence and a primordial scar. Is the Kuiper Cliff the signature of a giant, undiscovered world, a testament to our own ignorance of what shares our Sun's domain? Or is it the final, silent marker of how our system began, a boundary written in ice at the dawn of time? The silence of the cosmos is perhaps its loudest message. With hundreds of billions of stars in our galaxy alone, and most of them likely hosting planets, the universe seems to offer countless opportunities for life to arise. The numbers are overwhelmingly in favor of other beings sharing this vast expanse with us. Yet when we listen, we hear nothing but a profound and unnerving quiet. This is the heart of the Fermi paradox, a mystery captured in a single, deceptively simple question. Where is everybody? The physicist Enrico Fermi first posed it over lunch in the 1950s, and it has haunted science ever since. The contradiction is staggering. On one hand, the sheer scale and age of the universe suggest that intelligent, spacefaring civilizations should be common. The Milky Way is over 13 billion years old, providing more than enough time for such societies to have arisen, spread, and colonized entire galactic arms. The cosmos should be teeming with their activity, buzzing with signals and interstellar traffic. Our sky should be filled with the light of their engineering. Instead, we observe a natural, seemingly untouched universe. One chilling solution is the Great Filter hypothesis. This idea suggests that there exists some kind of barrier, an evolutionary or technological challenge so difficult that almost no life form can overcome it. This filter could lie in our past, a step that we somehow managed to pass but that extinguishes nearly all other life. Perhaps the jump from simple prokaryotic cells to complex eukaryotic life is astronomically rare. Or maybe the development of tool using intelligence itself is a freak accident. If the filter is behind us, we might truly be alone, the sole survivors of a cosmic lottery. The more terrifying possibility is that the Great Filter awaits us in our future. Perhaps every advanced civilization eventually creates the technology for its own destruction, whether through environmental collapse, runaway artificial intelligence, or nuclear war. In this scenario, the silence we hear is the graveyard of countless species who reached our stage of development and then vanished. We would be listening to the echoes of our own potential fate. Other solutions are less apocalyptic but equally mind-bending. It could be that intelligent life is common, but it chooses to remain hidden. A civilization that survives for millennia might develop a preference for silence, avoiding the risks of broadcasting its existence to a potentially dangerous galaxy. They could be all around us, observing from a distance, their technology so advanced and subtle that it is indistinguishable from the natural background of the universe. Another possibility is that we are simply too primitive to perceive them. An advanced culture might communicate using technologies we cannot yet conceive of, perhaps manipulating dark matter or using quantum entanglement in ways that are as invisible to us as radio waves would be to a medieval peasant. Their conversations could be happening all around us, woven into the fabric of space-time, and we lack the senses to even notice, or perhaps we are looking in the wrong place. We tend to imagine aliens living on planets like Earth, but life could thrive in environments we consider utterly hostile, from the deep atmospheres of gas giants to the subsurface oceans of icy moons. Their existence and their works might be so fundamentally alien that we would not recognize them even if they were right in front of us. The silence, then, is not empty. It is filled with questions about our own survival, our technological adolescence, and the ultimate nature of intelligence in the cosmos. Are we the first to ask these questions, the lonely pioneers of a silent galaxy? Or are we the newcomers shouting into a jungle full of hidden listeners who have long since learned to stay quiet? While we ponder the silence of a potentially populated cosmos, a single, flickering star reminded us that some cosmic mysteries might be built. In 2015, citizen scientists flagged a star in the constellation Cygnus that was doing something utterly bizarre. Its light was not just dimming periodically like a planet passing in front, but it was dipping in wild, unpredictable, and dramatic ways. At times, its brightness would drop by over 20%, a staggering amount of light being blocked, and then it would just as erratically return to normal. This was KIC 8462852, soon to be known as Tabby's star, after the astronomer Tabitha Boyajian who led its investigation. The data was so strange that it defied all conventional explanations. A planet, even a giant one, would cause a symmetrical, repeating dip. This was chaotic, like a swarm of objects of all different sizes and shapes were swarming around the star in a complex, untidy dance. The hunt for a cause ignited a firestorm of speculation. The first natural explanation was a massive family of comets. Perhaps a huge cloud of icy bodies, along with their long, dusty tails, was periodically obscuring the star. The sheer number required, however, would be almost unimaginable, a cometary armada on a scale never before seen. This led to a much more exciting, if far-fetched, idea. What if the dimming was caused by an alien megastructure? The concept, first proposed by physicist Freeman Dyson, is a Dyson sphere, a vast swarm of energy-collecting satellites built by a Type II civilization to harness the entire power output of its star. Such a structure, under construction and incomplete, would indeed block starlight in the irregular, massive ways observed at Tabby's star. For a thrilling moment, it seemed we might have found evidence of intelligence on a scale that dwarfed our own. The star became a global sensation, a beacon of possibility. Subsequent observations, however, began to cool this interstellar fever dream. Detailed studies across multiple wavelengths of light held the key. If a solid object like a megastructure were blocking the light, it would dim the star equally at all colors. Instead, astronomers found that the dimming was more pronounced in blue light than in red light. This is a classic signature of dust. Tiny particles smaller than a grain of sand scatter and block blue light more effectively, just like our own atmosphere makes the sky appear blue. The most likely culprit, then, is a vast, uneven cloud of fine circumstellar dust orbiting the star in a complex, clumpy ring. But the mystery is not fully solved. This is not ordinary dust. Its behavior is still highly unusual, requiring a strange and dynamic origin story. Perhaps a planet was recently shattered in a colossal collision, its debris still settling into a disk. Or maybe the star itself is going through a peculiar phase, actively expelling clouds of dusty material. The data has ruled out a solid, planet-sized megastructure, but it has left us with a new, equally compelling puzzle. Why is this one star shrouded in such a bizarre and dramatic veil? The answer reminds us that nature's imagination often exceeds our own, crafting mysteries that are wondrous not because they are alien, but because they reveal the endless, strange variety of the cosmos. Deep within the faint glow of the universe's first light, a pattern emerges that seems to look back at us. This is the axis of evil, a name that perfectly captures the unsettling nature of a discovery within the cosmic microwave background. This ancient afterglow, the leftover heat from the Big Bang, should be the most random and isotropic thing in the entire cosmos. Its hot and cold spots, the seeds of all future galaxies, should be scattered across the sky with no preferred direction, like a television screen displaying pure, random static. Yet, when scientists created a detailed map of this radiation, they found something deeply disturbing. The patterns of these temperature fluctuations appear to be subtly aligned with the plane of our own solar system. It is as if the grandest blueprint of the entire universe, a relic from a time before planets or stars existed, somehow knows which way is ecliptic up. This alignment defies the core principle of cosmology, the Copernican principle, which states that we do not occupy a special or privileged place in the universe. The cosmos should not care that we are here, and it certainly should not arrange its most fundamental structures to match the arbitrary plane in which our planet happens to orbit. The statistical unlikelihood of this happening by pure chance is staggering, making it one of the most controversial anomalies in all of modern science. So what could possibly explain this eerie cosmic coincidence? One possibility is that it is not cosmic at all, but a local contaminant, perhaps dust within our own solar system, or even a subtle systematic error in our instruments, is imprinting this false pattern onto the data, creating a ghost in the machine that mimics a fundamental flaw in reality. If it is real, the implications are profound. It could mean that the universe has a preferred direction, a fundamental lopsidedness that challenges Einstein's cosmological principle. Or, even more radically, it could be a sign that our universe is not infinite and uniform, but is part of a much larger, structured multiverse, and the axis of evil is a bruise left from a collision with another universe in the distant past. This anomaly forces us to confront a humbling possibility. Are we seeing the first crack in our standard model of cosmology, or are we simply seeing our own reflection, a phantom of our local environment, projected onto the grandest canvas of all? A black hole is not just a cosmic vacuum cleaner. It is a place where the two great pillars of modern physics, Einstein's general relativity and quantum mechanics, collide in a paradox so profound it threatens to shatter our understanding of reality itself. This is the black hole information paradox, and it begins with a simple, devastating question. What happens to the information about an object when it falls in? In our everyday world, information is never truly lost. If you burn a book, its pages turn to ash and smoke, a seemingly irreversible process. Yet, in principle, a being with perfect knowledge could collect every particle of soot and wisp of gas, reverse the chemical reactions, and reconstruct the exact book down to every comma on every page. Quantum mechanics insists on this principle. Information, the unique quantum state of every particle, must be preserved. It can be scrambled beyond recognition, but it can never be erased from the universe. Now imagine throwing that same book into a black hole. According to Einstein's general relativity, the book would cross the event horizon, the point of no return, and be utterly lost. All the information it contained, the story, the author's name, the very atoms that made it, would be crushed into the singularity at the center, permanently erased from our universe. The black hole would then, according to Stephen Hawking's great discovery, slowly evaporate by emitting a faint glow of particles, now known as Hawking radiation. This radiation, however, is purely thermal. It is random, featureless heat like the steam rising from a cup of coffee. It carries no information about what fell in, whether it was a book, a star, or a million elephants. When the black hole finally evaporates completely, all that remains is this bland, informationless radiation. The information about the book is gone forever. This is the paradox. Quantum mechanics says information cannot be lost. General relativity, combined with Hawking's work, says the black hole destroys it. Both theories are spectacularly successful in their own domains, but here, at the edge of a black hole, they give mutually exclusive answers. One of them must be wrong. So where does the information go? One radical idea is the holographic principle. It suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon like a cosmic DVD. The three-dimensional interior of the black hole is a projection of this information stored on its two-dimensional surface. When the black hole evaporates, this information is somehow imprinted onto the Hawking radiation, released back into the universe in a scrambled but recoverable form. The universe, in this view, might itself be a hologram. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space as relativity suggests, but a searing wall of high-energy particles. The moment an object touches the horizon, it is instantly incinerated. This fiery death would release all its information back out into the universe immediately, resolving the paradox but at a terrible cost. It means that the event horizon, as Einstein described it, does not exist, forcing us to abandon one of the core predictions of general relativity. Are we standing at the edge of a smooth portal to another realm, or a blazing wall of cosmic energy? The answer will rewrite the laws of physics, revealing whether information truly is immortal, or if some places in the cosmos are capable of erasing the very story of existence. At the heart of the black hole paradox lies a deeper conflict, a fundamental crack in our understanding of the cosmos. We have two rule books for how the universe works, and they are written in completely different languages. Einstein's general relativity gives us the grand cosmic stage, describing gravity as the elegant warping of space-time, dictating the dance of planets and the expansion of the universe. Quantum mechanics gives us the script for the actors on that stage, the bizarre, probabilistic world of atoms and particles. Both theories are spectacularly successful in their own domains, yet they are utterly incompatible. The search for a theory that can marry them, a theory of quantum gravity, is one of the greatest quests in all of science. This is more than an academic exercise. It is an attempt to understand what reality is at its most fundamental level, especially in extreme environments like the first moment of the Big Bang or the center of a black hole, where both immense gravity and quantum effects reign supreme. Two leading candidates offer wildly different visions of this unified reality. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy or strings. Just as a single violin string can vibrate at different frequencies to produce different musical notes, these cosmic strings vibrate in different ways to produce all the different particles we see, from electrons to quarks. In this view, gravity is just another note in the cosmic symphony. The challenge is that these strings are thought to be so small that testing the theory directly is currently beyond our reach. The other major approach is loop quantum gravity. It takes a different path, suggesting that space-time itself is not smooth and continuous, but is woven from a fabric of tiny, finite loops. Picture the fabric of reality as a chainmail tunic, a network of interconnected links. This quantized space-time would have a granular structure, a pixelated reality at the tiniest possible scale, the Planck length. This theory naturally avoids the infinities of a singularity. implying that the Big Bang was not a true beginning but a great bounce from a previous universe. This quest for quantum gravity is a stepping stone to an even grander ambition, the dream of a theory of everything. Physicists seek a single, elegant framework that unifies all four fundamental forces of nature into one master equation. We have already achieved a partial unification. The electromagnetic force and the weak nuclear force were successfully merged into the electroweak force. Our current best model, the Standard Model of Particle Physics, describes three of the four forces, the strong nuclear, weak nuclear, and electromagnetic, with breathtaking precision. But gravity remains the stubborn outsider, refusing to join the party. A true theory of everything would weave gravity into this tapestry, providing a single, coherent description of the universe from the smallest quark to the largest galaxy cluster. It would be the ultimate key, unlocking the deepest secrets of existence. Yet this pinnacle of physics remains elusive. The mathematics is ferociously complex, and the energy levels required to test these ideas are far beyond anything we can create. Are we on the verge of a revolution that will reveal the universe as a hologram, a vibrating string, or a spin foam? Or is reality, in its infinite subtlety, hiding a truth more beautiful and strange than any theory we have yet dared to imagine? Even the universe's first moments left a forensic trace we cannot fully decipher. The Big Bang was not just an explosion of space, but a cosmic forge, a brief, searingly hot period where the first atomic nuclei were hammered together. This process, known as Big Bang nucleosynthesis, produced the universe's initial stock of hydrogen, helium, and a tiny trace of lithium. For the most part, our calculations of how much of these elements should have been created match the ancient, pristine stars we observe. Yet for one specific isotope, lithium-7, the numbers are catastrophically wrong. Our most sophisticated models of the early universe predict about 3 times more lithium than we actually find in these celestial fossils. This is the lithium problem, a small number with enormous implications, suggesting a fundamental flaw in our story of creation. How could the universe's recipe be so precise for some ingredients and so wildly off for another? The discrepancy is not a minor rounding error. These ancient stars act as cosmic time capsules, their atmospheres preserving the chemical composition of the early cosmos before later generations of stars began to pollute the mix with their own nuclear ash. When we analyze their light, the spectral signature of lithium-7 is consistently, stubbornly weaker than it should be. It is as if someone went into the universe's pantry shortly after it was stocked and secretly threw away 2 out of every 3 lithium atoms. So where did the lithium go? One possibility is that our understanding of nuclear physics in that first frantic 3 minutes is incomplete. Perhaps there were unknown nuclear reaction pathways or resonances that destroyed the lithium as quickly as it formed, a process we have not yet accounted for in our laboratories. The other, more thrilling possibility involves entirely new physics. What if an unknown type of particle, a relic from the universe's earliest moments, interacted with the primordial nuclei and effectively ate the missing lithium? One candidate is a hypothetical particle known as the action, which we already suspect might be a component of dark matter. These particles could have altered the nuclear reactions just enough to suppress the lithium yield. Another idea involves supersymmetry, a theory proposing that every known particle has a heavier shadow twin. The decays of these supersymmetric particles in the early universe could have produced just the right amount of destruction to resolve the mismatch. This tiny lithium deficit is a massive clue. It tells us that the pristine environment of the Big Bang might have been host to actors we have not yet met, particles or processes that left their signature only on this one fragile element. Solving this mystery requires looking backward and inward simultaneously, studying the oldest stars in the sky while also smashing particles together in underground colliders. The fate of those missing atoms holds the key to a deeper truth. revealing whether our standard cosmic model is merely unfinished or if it is quietly hiding an entire new chapter of physics. But this cosmic web is not woven evenly. Stretching across an unimaginable volume of space, a region of profound emptiness challenges our very understanding of cosmic structure. This is the Boötes void, a spherical chasm of near-nothingness so vast it could contain thousands of galaxies like our Milky Way, yet holds only a handful. If you were to place our galaxy at its center, the nearest major galaxy would be so far away its light would take millions of years to reach us, leaving our night sky almost perfectly black. This void is not a complete vacuum, of course. Space is still filled with the thin soup of hydrogen and the faint glow of the cosmic microwave background. But the grand structures we expect, the glittering cities of stars, are almost entirely absent. How does a region of space hundreds of millions of light years across manage to avoid the party? According to our models of the early universe, matter should be distributed in a web-like pattern, but the sizes of the voids and filaments should fall within a certain statistical range. The Boötes void is an outrageous outlier, a cosmic desert on a scale that seems to defy the natural grain of the cosmos. It is simply too big. One leading theory suggests it was not born as a single, giant emptiness, but grew over eons through a process of cosmic cannibalism. In the intricate dance of the cosmic web, gravity pulls not only matter together but also pushes emptiness apart. Smaller, adjacent voids can gradually merge, their boundaries dissolving as the galaxies on their edges are pulled toward denser filaments. Over billions of years, these merging voids can create a single, colossal emptiness, a supervoid whose immense scale is a product of its long and quiet history. Another, more speculative idea involves dark energy, perhaps in regions where the density of matter was initially just a little bit lower. Dark energy's repulsive force got a head start, pushing the few nascent galaxies apart more effectively and accelerating the creation of the void. The existence of the Boötes void forces us to ask whether our universe is truly as uniform as we believe, or if it contains freak regions of emptiness so vast they should not, by our best calculations, even be there. Is this void a statistical fluke, a 1 in a trillion cosmic lottery ticket for nothingness, or is it a sign that the forces shaping our universe are even more complex and unpredictable than we have dared to imagine? While our own solar system holds worlds of familiar beauty, one of its most bizarre features spins in plain sight. At Saturn's North Pole, a perfect gargantuan hexagon has been etched into the atmosphere, a geometric cloud pattern so precise it seems engineered. This six-sided jet stream, wider than 2 Earths placed side by side, has persisted for decades, a stable and violent storm of unimaginable scale. It is a feature utterly unique in our solar system, a puzzle written in wind and cloud. Scientists have turned to giant rotating tanks of fluid, creating miniature laboratories to simulate Saturn's turbulent, gaseous atmosphere. In these experiments, when a small, circular obstacle is placed in the center of a spinning fluid, instabilities can sometimes form polygonal shapes, including hexagons around it. This suggests the hexagon is a standing wave pattern, a stable ripple in the fast-moving jet stream, perhaps anchored by some deep, unseen atmospheric structure or a massive hurricane at the very pole. Supercomputer models can now recreate a hexagonal shape, but they struggle to explain its razor-sharp edges and incredible longevity. Why 6 sides? Why has this one particular geometric form remained locked in place, resisting the chaos that defines the rest of Saturn's swirling, banded atmosphere? The hexagon defies the very nature of fluid dynamics, which tends toward turbulence or gentle curves, not hard-edged, persistent polygons. It is a natural wonder that feels profoundly unnatural, a cosmic signpost pointing toward atmospheric physics we have yet to fully comprehend. What other secrets about the flow of matter and energy are hidden within that perfect, spinning shape? a strange visitor from the depths of interstellar space offered a new kind of cosmic mystery. In October 2017, astronomers in Hawaii spotted an object moving at such a high speed that it could only have come from beyond our solar system. They named it Oumuamua, Hawaiian for scout or messenger from the distant past. It was the first confirmed interstellar object ever detected, a piece of another star system passing through our own. But its properties were anything but ordinary. First, there was its shape. Based on how its brightness changed dramatically as it tumbled, scientists inferred it was highly elongated, perhaps 10 times as long as it was wide. This made it unlike any asteroid or comet we had ever seen in our own solar system, a cosmic cigar tumbling silently through the void. The second and more baffling characteristic was its motion. As Oumuamua sped away from the Sun, it exhibited a slight but definite non-gravitational acceleration. It was moving just a tiny bit faster than the Sun's gravity alone could account for. This is common for comets, as the Sun's heat vaporizes their icy surfaces, creating jets of gas that act like a natural rocket engine. The crucial detail is that this outgassing also produces a visible coma, a fuzzy envelope of gas and dust around the nucleus. Oumuamua had no coma. Telescopes pointed at it saw only a bare, dark, and silent rock with no visible signs of cometary activity. So what was pushing it? The scientific debate ignited, spanning the spectrum from the plausible to the extraordinary. One leading natural explanation proposed it was a strange type of comet after all, composed largely of solid nitrogen ice. As the Sun warmed it, chunks of this exotic iceberg could have sublimated directly from solid to gas, providing the thrust without releasing the fine dust that creates a typical dusty coma. Another idea suggested it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and light that radiation pressure from the Sun itself could have given it the extra push. Then there was the more speculative hypothesis. Could Oumuamua have been an artificial object, a piece of alien technology like a light sail? Its unusual shape and the peculiar nature of its acceleration made it, for a brief moment, a candidate for something built by an intelligence. While most scientists strongly favor a natural origin, the very fact that the possibility was seriously discussed highlights just how strange this object was. The true frustration is that Oumuamua was already on its way out when we found it, a fleeting ghost in our cosmic neighborhood. We had only a few weeks to observe it before it vanished back into the darkness from which it came. Its brief visit left us with more questions than answers, a tantalizing hint that our galaxy may be filled with such strange travelers, future observatories like the Vera C. Rubin Observatory are poised to find many more of these interstellar visitors, giving us the chance to study them in detail before they slip away. The mystery of Oumuamua is a promise of future discovery, a signal that the universe is still full of objects that defy our expectations, waiting just beyond the edge of our vision. Magnetic fields weave through the cosmic void, an invisible force connecting the vast emptiness between galaxies. This 23rd mystery asks how magnetism came to rule such immense domains. We find these fields everywhere, from the spiral arms of our own Milky Way to the colossal gaps separating entire galaxy clusters. Their presence on such a grand scale is deeply puzzling because the primordial universe was likely a placid, unmagnetized sea of plasma. There was no obvious cosmic battery to generate the first currents. So how did these invisible lines of force emerge to stitch through the fabric of intergalactic space? The leading theory points to a tiny seed. In the turbulent plasma of the early universe, minuscule magnetic fields could have been born from the chaotic motions of charged particles. Think of it like a single, weak bar magnet appearing in an otherwise non-magnetic material. This faint primordial seed would have been stretched and amplified over billions of years by the motion of cosmic gas acting like a dynamo. As galaxies formed and rotated, their swirling motions could have twisted these weak initial fields, strengthening them and eventually ejecting them into intergalactic space through powerful winds from supernova and active galactic nuclei. These cosmic engines, particularly the supermassive black holes at galaxy centers, can pump tremendous energy into their surroundings, potentially magnetizing vast volumes of the cosmos. Yet this story faces a colossal challenge of scale. The process of building a magnetic field from a tiny seed is slow and inefficient. Could it really have filled the universe's largest voids in the time available? Some scientists propose a more dramatic origin, where magnetic fields were born in the extreme violence of the Big Bang itself, woven into the cosmos from its very first moments. Others suggest they were generated later by the shock waves from the first generation of supermassive stars, whose explosive death rattled the infant universe. The truth remains suspended between these ideas. Are we seeing the amplified whisper of a primordial seed, or the accumulated echo of countless stellar explosions? These cosmic magnetic fields are more than a curiosity. They are a fundamental part of the cosmic ecosystem, influencing how gas cools to form new stars and guiding the paths of high-energy cosmic rays. Their silent, pervasive presence is a reminder that the emptiness of space is not empty at all, but structured by forces whose origins are still written in the dark. The most precise measurements in cosmology are telling us two different stories about the universe's expansion, and the plot is only thickening. We must return to the Hubble tension, the stubborn disagreement over how fast the cosmos is growing. On one side is the SH0ES collaboration, which uses the cosmic distance ladder to measure the present-day expansion rate. They observe Cepheid variable stars whose predictable pulsing reveals their true brightness, and Type 1, a supernova, the brilliant standard candles that allow them to gauge distances to far-off galaxies. Their data is meticulous, their error bars shrunk to a fine point, and their result is a specific high value for the Hubble constant. On the other side is the Planck satellite, which studied the infant universe by mapping the cosmic microwave background. Its measurements are also exquisitely precise, but they yield a consistently lower value for the expansion rate. This is not a small squabble. It is a fundamental clash between the universe as it was and the universe as it is, a direct challenge to our standard model of cosmology. The discrepancy has now reached a significance level of 5 sigma, a threshold in physics that often signals a real discovery, not a mere statistical fluke. So why does this gap persist even as our tools grow sharper? The debate often centers on the methods themselves. Could there be an unaccounted for systematic error in the distance ladder? Perhaps our understanding of Cepheid stars is incomplete, or maybe supernovae are not quite as standard as we assume. Conversely, the Planck results rely on the assumption that our lambda CDM model, which includes dark matter and a cosmological constant, is the complete and correct description of the universe. What if it is not? This is where the potential for new, revolutionary physics enters the stage. One compelling idea is early dark energy. This theory proposes that a temporary form of dark energy existed in the universe's first few 100,000 years, an extra repulsive force that altered how sound waves propagated in the primordial plasma. This would change the interpretation of the Planck data, tweaking the predicted expansion rate to align more closely with the SH0ES measurement. Another possibility involves neutrinos. What if these ghostly particles, which stream through the universe almost untouched, have unusual properties? If they interact with each other or with dark matter in ways we have not predicted, it could affect the growth of cosmic structures and, in turn, resolve the tension. The Hubble constant tension is now one of the most pressing issues in all of science because it refuses to go away. Its resolution promises more than just a single number. It could unveil a new component of the cosmos or force us to rewrite the rules governing the universe's evolution. We are caught between two impeccable measurements, each pointing toward a different cosmic reality, and the choice between them may redefine our understanding of everything. The final mystery is the fate of time itself. All the cosmic puzzles we have confronted, from the push of dark energy to the pull of the great attractor, lead to this ultimate question: how will the universe end? The answer hinges entirely on the unknown nature of the force driving cosmic acceleration, and it presents us with two starkly different finales. The first is the Big Freeze, a long, slow fading into oblivion. In this scenario, dark energy remains a constant, gentle pressure, continuing to push galaxies apart at an ever-increasing rate. Over trillions of years, the fuel for new stars will be exhausted, and existing stars will burn out one by one. Galaxies will drift apart until each is an isolated island in an ever-cooling void. Black holes will eventually evaporate via Hawking radiation, and the universe will approach a state of maximum entropy, a uniform, frigid sea of diluted particles and radiation where no work can be done, no structure can form, and no new event of any significance will ever occur again. It is a quiet, heatless death. The alternative is far more violent and immediate. If dark energy is not a constant but a force that grows stronger over time, a quintessence field that intensifies, the result is the Big Rip. In this cataclysm, the repulsive force would eventually overcome gravity itself. First, the cosmic web would be shredded, tearing galaxy clusters apart. Then, the gravitational glue holding individual galaxies together would fail, sending stars flying into the expanding darkness. As the force strengthens, it would tear stars and planets apart. In the final, horrific moments, just before time itself loses all meaning, the overwhelming force would rip apart atoms, nuclei, and even the fabric of space-time. The universe would end not with a whimper, but with a catastrophic, fundamental unraveling of reality. The choice between these two destinies is written in the properties of dark energy, a mystery we have yet to solve. Will our cosmos drift into an eternal, silent night, or will it be annihilated in a final, blinding flash? The ultimate story of our universe remains an unwritten page, its final word a secret the cosmos still keeps. Our cosmic search is about to gain powerful new eyes. A new generation of observatories, both on the ground and in space, is preparing to probe the universe's deepest secrets with a sensitivity we have never before possessed. The James Webb Space Telescope, with its immense golden mirror, is our infrared window to the dawn of time. It peers through cosmic dust to witness the formation of the very first stars and galaxies, seeking to understand how the primordial darkness gave way to light. But its mission extends further, analyzing the atmospheres of distant exoplanets for the chemical signatures of life, and studying the faint, ancient light that could reveal the properties of dark matter by how it distorts the images of faraway galaxies. On a mountaintop in Chile, the Vera C, Rubin Observatory will conduct a relentless 10-year cinematic survey of the entire southern sky. Its enormous camera will capture the universe in motion, night after night, spotting fleeting events and tracking subtle changes. This monumental effort will map the cosmos in unprecedented detail, tracing the distribution of dark matter through gravitational lensing on a colossal scale, and discovering millions of new solar system objects, potentially including the hypothesized planet 9 or more strange interstellar visitors like Oumuamua. Then there is LISA, the Laser Interferometer Space Antenna, a mission that will listen to the universe in an entirely new way. Instead of light, it will detect gravitational waves, the ripples in space-time caused by the most cataclysmic events. While ground-based detectors have heard the collisions of black holes and neutron stars, LISA 3 spacecraft, flying in a perfect triangle millions of kilometers apart, will tune into the low-frequency hum of the cosmos. This will allow it to hear the mergers of supermassive black holes, potentially sense the cosmic strings left over from the Big Bang, and even capture the faint whisper of primordial gravitational waves from the epoch of inflation itself. This last capability is the ultimate goal, a direct test of the theory that the universe underwent a violent exponential growth spurt. If LISA can detect the specific fingerprint of these waves imprinted on the gravitational background, it will provide the first direct evidence for inflation, revealing what powered the universe's birth. Together, these instruments form a synergistic arsenal against the unknown. James Webb will show us the infant universe in stunning clarity, Vera C. Rubin will map its adult structure and dynamics, and LISA will listen to the vibrations of its very fabric. They are not just telescopes, they are time machines and cosmic historians, designed to collect the precise data that could finally crack the codes of dark energy, dark matter, and our own cosmic origins. The answers to our 25 mysteries may not lie in a single revelation, but in the flood of new, inexplicable data these machines are destined to bring. What will we see when we finally look at the universe with eyes sharp enough to see its deepest truths? These cosmic puzzles are far more than intellectual curiosities. They are fundamental to our very sense of reality. Understanding why the universe expands as it does and what its ultimate fate will be is the ultimate context for our own existence. Are we living in a cosmos destined for an eternal, silent freeze or a violent, sudden rip? The answer to that question dictates the entire future narrative of everything, placing our fleeting human lives against a backdrop of almost unimaginable time and scale. This pursuit anchors us, giving us a cosmic address and a story that stretches from the first moment of creation to the very last. It forces us to confront our profound connection to the universe, for the atoms in our bodies were forged in the hearts of long-dead stars. We are not just living in the universe is living within us, and to understand it is, in a very real sense, to understand ourselves. This philosophical drive is matched by intensely practical benefits. The quest to map dark energy or detect dark matter has consistently pushed the boundaries of technology, leading to innovations that ripple through our daily lives. The need to process the immense data from sky surveys like the one the Vera C. Rubin Observatory will conduct has driven advances in computing and artificial intelligence. The exquisite optics developed for telescopes like the James Webb Space Telescope have found applications in improved medical imaging, leading to more precise laser eye surgery and earlier cancer detection. Even the World Wide Web was created at CERN to help physicists share their data, a spin-off that has since reshaped human civilization. Each time we reach for the stars to answer a fundamental question, we build better tools for understanding our own world. The search for our cosmic fate is not a detached academic exercise. It is a journey that continually gives back, weaving new threads of knowledge and capability into the fabric of human society. What other wonders will we invent, not because we sought a new gadget, but because we dared to ask the universe what it is made of? 25 cosmic enigmas have led us on a journey from the ghostly pull of dark matter to the phantom push of dark energy. We have stood at the edge of black holes where information itself may be destroyed, and we have listened to the profound silence of the cosmos, wondering if we are alone. We have seen perfect hexagons etched into alien skies and traced the invisible rivers of galaxies flowing toward an unseen attractor. These are not isolated curiosities, but interconnected threads in a single grand tapestry, the story of an expanding universe that is still being written. The most thrilling realization is that this story is not finished. Every one of these mysteries, from the lithium deficit in the first stars to the strange acceleration of Oumuamua, represents a frontier of human knowledge. They are open doors, not closed chapters. The cosmos is a living puzzle, and we are the detectives, armed with ever more powerful tools and an insatiable curiosity. So the next time you find yourself under a clear night sky, look up. Remember that the faint starlight reaching your eyes is a messenger from the distant past, and the darkness between those stars holds secrets we are only beginning to grasp. Our journey to understand the universe is the greatest adventure we can undertake, a quest that redefines our place in the cosmos and continually reminds us of the wonder that lies just beyond the edge of our understanding. Stay curious, for the next great discovery is waiting.